Hello everyone, this is my second video on direct current control. Today we're going to be making a practical circuit which is going to be an LED driver, and we're going to be following on from the principles we learnt in the first video, taking a look at inductors and how they can be used to smooth current. As you can probably hear, I'm a bit unwell, but I'm going to soldier through it for you guys, and I'm afraid you're just going to have to put up with this irritating croaky voice for today. Anyway, let's get right into it. So here's the circuit from the last video, and there's not really very much that we're going to have to change. All that we need to do is add in the comparator that's going to be measuring the current going through the inductor and comparing it to the reference value that we've set. And the output of that comparator then just controls the MOSFET. To measure the current through the inductor, we're going to need to add a shunt. So just a low value resistor, and we can measure the voltage across it, and the voltage across it will tell us the current. So for example, if we used 1 ohm, then if there was 2 volts across it, that would mean there's 2 amps flowing through it. And instead of modifying the circuit from last week and adding in the comparator, I'm going to just start again making a new circuit because I also want to use a different inductor. So the circuit we're going to make today is going to be, I'm going to make it on this variable board using this MOSFET to switch, which is the same as the one we used last week. I'm going to use this diode, which is a bit chunkier. It's TO220 instead of just a sort of traditional axial package. And this is the flyback diode in the circuit. Then we're just going to use a normal cheap gate drive, the same as last week as well. And the comparator is going to be an LM393, which is basically all that I have. It should hopefully be fast enough. The thing that this circuit's going to be controlling is this LED. So it's a high power LED that's meant for, I can't remember the proper name for it, but a grow light basically. So it looks very purple, the light, and it's basically the ideal spectrum for growing plants. And I've put a little heatsink on the back because it's a 3-watt LED. And the final thing to look at is the inductor. So I made this inductor specially for this circuit. And the main reason why I'm not using the one from last time is, well, 2 reasons. Firstly, this one can handle much higher current. So the windings can probably take about 15 amps, but it hasn't got a gapped core. So the saturation current is only about 1 amp, which should be fine for this LED and other things I plan on running later. Crucially, it's got a pretty high inductance, so I think it's about 350 millihenry. And the reason why that's important is the higher the inductance, as we saw in the last video, the slower the current will increase and decrease. And that means the slower we have to switch our MOSFET. And I think the combination of the comparator I'm using and the MOSFET I'm using, we probably can't switch much higher than maybe 200 kilohertz. And I think if we used a very small inductor with a low inductance, we'd have to switch quite a lot faster than that. I'll quickly show you how I tested the saturation current of this inductor. What I did is I used a circuit I've made, I'm calling the saturator. And basically it's just got 2 supplies, so you've got a supply for the gate drive and a main supply. And we're about 15 volts for the gate drive. The main supply voltage can change depending on basically what inductor you've got connected. But right now it's at about 12 volts. And basically it just charges a big capacitor. I've also got some surface mount capacitors on the back so that I can have a lower ESR. And then all that happens is when you press this button, it turns on the MOSFET for I think about 10 microseconds. You can adjust it with this trimmer, and moving this jumper switches between 2 different ranges. So there's quite a lot of variability in the width of the pulse this produces. And basically it just puts a big high current pulse through the inductor, and then looking at it on a scope you can see where it saturates. So here's the circuit with the inductor connected just on these output terminals. There's 3 different pairs of test points, so you can test IDS, so the drain source voltage of the MOSFET. That's the most interesting one for testing inductors because that's the current that goes through it. There's also VDS and VGS, which are more for testing the MOSFET really. With VDS and IDS you can work out the switching losses, and with VGS you can analyse how the gate drive is working with the MOSFET. So here's the inductor current on the scope, and what I've done is instead of single shot I've put it in normal mode, so that every time I press the button on this circuit I can get a new sample. And you can see occasionally it reads a bit weird. Mostly that's because of button bounce on my circuit, but I didn't bother getting rid of that because all you'd have to do is press the button again to get a nice reading. But it really illustrates inductor saturation quite nicely. So if I zoom in and scroll along a bit, You can see here the current slowly rises, and then there's this sort of elbow and it suddenly shoots up. So here we are at 500 milliamps per division, and you can see it goes up half an amp, 1 amp, still pretty much linear, and then after 1 amp it starts to shoot up. And that's because the ferrite core is saturated. It can't take any more flux. So the inductance drops off massively, so then there's nothing to limit the current and the current shoots up. Now what I can do is a combination of increasing the supply voltage and widening my pulse, just to show off my circuit and how high current it can get. There we go. So this is actually at 20 amps per division, so we're getting 20, 40, 60, over 80 amps, which means this can saturate basically any inductor. And for such a small, simple circuit, I'd really recommend making one if you work with magnetics much at all. In case you're wondering, this voltage roll-off is because I don't have a huge amount of capacitance in this circuit, so I can dump 80 amps into the inductor, but then this is the capacitors discharging. If you wanted higher currents and you wanted to keep it flat so it didn't have this roll-off, then you just need to use a lot more capacitance. But the ESR is quite important, so if you wanted to do this nicely, maybe use polymer or film caps, or a lot of multi-layer ceramics. In this particular circuit as well, this peak current of 80 amps is actually limited by the MOSFET on resistance. So, as I said, you can monitor VDS, which is the drain source voltage of the MOSFET, which should be close to 0 when it's turned on. But in this case, the drain source voltage actually reaches about 25 volts with a 30 volt supply. And that's basically just because with this MOSFET, even with a gate source voltage of 15 volts, the on resistance is still quite high, so once you've got 80 amps flowing through it, that on resistance has reached sort of 150, 200 milliohms, hence why it's got such a big voltage across it. So based on that saturation current, I've made this very messy schematic, which I'll put a tidier version on the screen now. But what we have is, going from left to right, far left we have the flyback diode, and that's just to keep the current flowing when we turn our MOSFET off. You can see the MOSFET down at the bottom, along with its accompanying gate drive circuitry. Then going up we have the inductor in series with the LED, or whatever else we decide to connect to the output. And then at the top we have the shunt. So with a shunt you can either have a low side shunt, a high side shunt, you can put it anywhere basically, as long as it's in series with the inductor. And for me, I thought having it at the top supply is probably simplest. Then this is the current adjustment circuit along with the hysteresis setting. So you can see a combination of this resistor and this potentiometer set the current, that's what this I is for, and then this H is for hysteresis. So again we have another resistor and another potentiometer, and this time this potentiometer adjusts the hysteresis range. I've also put a capacitor in here because this current target isn't going to be changing much. This will smooth the output from this potential divider. And this connection here is the output of the comparator. So now I'm going to build up this circuit using these components and putting them on this Vero board, and I'll be back when it's done. Right, it took my unwell brain a full 5 hours, but here we go, finished circuit. The hysteresis using the output of the comparator, I just couldn't really get it to work, so I've ended up using a second, slightly inferior technique, which is just having a low pass filter on the output of the shunt, which basically just adds a bit of delay. So essentially, instead of amplitude hysteresis, we've got time hysteresis. But overall it gives a very similar result, which I can now demonstrate. So it's a bit harder to show how the circuit works on Vero board compared to breadboard, but I'll give it a go. This terminal block on the right is our supplies. So we've got ground, and then we need two supplies. The gate drive and the comparator need a slightly higher voltage than the main power circuit. So this is running at 15 volts and this is running at 16.5 volts. That's just because the inputs of the comparator can't reach the upper rail because it's a bit of a shit comparator. Then we've got some decoupling caps. These three parallel resistors are operating as our shunt. They're 3.3 ohms each, so that gives us roughly 1 ohm. They're in parallel for the lower resistance and also for the power rating. This white wire is our shunt voltage, so that comes down to this trimmer. This trimmer's in series with this cap, which then feeds the comparator. So this trimmer can be used to adjust the time constant of the low-pass filter connected to the shunt. And that in turn will affect the hysteresis and the switching frequency of the circuit. These two terminal blocks on the left are in series, The idea is that you connect your inductor to one of them and your load to the other. Then here we have our MOSFET, and on the left of that we have our diode. The diode is the flyback diode for the inductor. That's what keeps the current flowing through the circuit when the MOSFET on the right turns off. The MOSFET is controlled by the gate drive here. Here's a gate resistor to limit the switching speed. Then here we have a second trimmer. This trimmer is used to set the target current. So one of the inputs to the comparator is the output voltage of the shunt, and the second input is the output voltage of this trimmer. And it will try and get the voltage across the shunt to match the voltage from this trimmer. So if we say that was 100 millivolts, that would then correlate to roughly 100 milliamps average current in the inductor. I've now connected the high power LED that I mentioned earlier to the output terminal block, and that's in series with the multimeter so that we can measure the current going through it. I've moved the camera and the focus a bit so that you can see the current through the LED, but then also importantly you can see the current coming from the power supply. Because if this was a linear circuit, the currents would be the same, but because this is very efficient, we can generate a higher current and put it through the LED compared to the current coming from the supply, which I can now demonstrate if I turn it on. So here you can see we've got 270 milliamps going through this LED, but we're only drawing 90 milliamps from the supply, because the supply is at a much higher voltage, so the power will end up being similar. I can now adjust the current with this trimmer, so I can turn it up. Let's see how high it'll go. So it looks like it'll let us go well over an amp output. I'm going to leave it at about 800 milliamps, as I'm not sure if the LED can take much more than that continuously. Here's a second multimeter so we can measure the voltage across the LED, which is 3.74 volts. From that we have a calculated efficiency of around 62%, which is not great, but it's a lot better than a linear circuit would be for driving such a low forward voltage LED with such a high current. The next thing I think that's worth looking at is the switching waveform. So at the moment we're switching at around 144 kHz. But because this doesn't use traditional pulse width modulation, varying the power, or varying the current I should say, also affects the frequency. So right now I'm reducing the current and you can see the frequency decreasing. I've now gone from 900 milliamps down to 200 milliamps, and the frequency has dropped off a bit. I'm going to use the software frequency measurement because the hardware one gets a bit confused with signals like this. It looks like the software one does as well. That's just because, as you can see, it's not switching very nicely, which is probably where a lot of our losses are coming from. I can also adjust the hysteresis range with the second trimmer. So now if I reduce the resistance in the feedback filter, we get a shorter time constant, which reduces our hysteresis. That also increases our switching frequency. This is at minimum load, which is putting about 80 milliamps through the LED. If I turn it down anymore, it just turns off. I'd probably ignore this switching frequency thing, and the same as the counter up there. It's a 40 microsecond period roughly, so around 25 kHz is what we're switching at the moment. I think that overall, despite the not brilliant efficiency, I'm still quite pleased with this circuit overall. It's a good demonstration of the constant current control, using a switching system which is much more efficient than a simple linear version. It also shows that just by using the comparator we can get rid of all the complicated control system that's often required in a circuit like this. And it gives me a lot of hope for what I'm planning on covering in the next video, which is basically expanding this a bit further to make a Class D audio amplifier. And speaking of that, with a switching frequency over 200 kHz, this circuit can respond very quickly to changes in current demand. So I think just to finish this video off, as a sneak preview to what could potentially be possible in the next video, I'm going to swap the current control trimmer for an external input, and we're going to see if we can do something interesting. Right, so what I've done now is I've bypassed this current adjustment trimmer, and instead I'm feeding in a voltage, which is coming from the noisy function generator that we used in the isolated voltage measurement videos. So hopefully it's somewhat in focus. You can see the voltage that's set on here. Now because it's a high side shunt, a negative voltage represents a current flowing through the LED. So you can see, if I turn this on, now I can just control the current straight from here. So that should be 10 milliamps, 20, 30, 40. That's the idea. And then we can get super precise with it as well. But you can see there's definitely a minimum level where the circuit won't work. And now maybe you can see the LED is sort of doing a strange flickering thing. That's when it's slightly too low current for the circuit to work reliably. But if I go from 3.1 to 3.2, now it's unstable. But this isn't really what I wanted to do, because that's not very interesting. What I've done is I've combined that with the obligatory DIY Lightning to BNC adapter. And through that what I can do is press play on my phone and have an LED that dances to my music. I don't know how well you'll be able to see, maybe more volume might help. I think you can see that there. So I'm basically playing music through my LED. That's not very interesting, but if I swap the LED for a speaker, maybe it will be. So I have this little test speaker that I keep behind my piles of power supplies, and I can use that to test amplifier circuits like this. So I just bring the lead along here, and I've got one end plugged into the constant current driver circuit, and the other end I can touch to the output. Now I've moved the speaker a bit, so hopefully you'll be able to hear what's coming out of it. What I'm going to do is I'm going to just hold this on the output and then press play on my phone. Just a quick warning, never use a circuit like this to drive a speaker, because especially if you want it to sound decent, you need a DC offset, which means there's a constant current flowing through your voice coil, which will probably burn out your speaker very quickly. In the next video I'll show how to do this properly. This is more just a proof of concept. So I can hold this on the output and press play, and so that I don't get copyright striked, I'm going to be using the new electro outro composed by yours truly. Sounds a little bit distorted, doesn't it? But now, because I've got the phone in series with the function generator, I can add a small offset, just enough so that we're basically biasing the circuit so that it's always in conduction, a bit like a normal class AB amplifier. As I say, this does mean it's bad for the speaker though. You can also hear quite a lot of noise coming out of it. Let's say overall this isn't too bad. You can recognise the song. It's definitely got a very poor frequency response though. And that's it for today's video. Hopefully you've been able to put up with this croaky voice, and hopefully you learned something from this circuit. The next video will probably be a bit more informative, and hopefully by then I'll have an explanation as to why the amplitude hysteresis system I originally tried to implement in this didn't work very well. Thank you very much for watching, and until next time, have a good one.